Welcome to qnawire.
Hi, so in this case, remember that for every amino acid, essentially what we have is a structure that is a CH, COOH, and H2, and then we're going to have a fragment that is the one that actually identifies every amino acid. In this case, for asparagine, the fragment in hand is CH2 and an amide group over here. But in this case, it really doesn't matter what fragment we have, since we're given the Ka corresponding to the COOH fragment, that is 6.92 times 10 to the minus 3. And we are told that we have in solution initially the form that has a minus 1 charge. Okay? So that means that I'm going to erase all of this section because that fragment cannot have a minus 1 charge. And the only possibility that we have for a minus 1 charge is to have this associated salt of the carboxylic acid. That means that the acid base reaction that we're actually looking at is the following. We're going to have our amino acid with a minus 1 charge form that is going to interact with water in order to generate a portion of COOH of the carboxylic acid plus OH minus. So my amino acid is going to act as a base in this scenario. With this, we can go ahead with our ice table. We are starting with 0.5 molar. Water doesn't matter because it doesn't enter into equilibrium. We have 0 and 0. The amount of change, we're going to calculate x, producing plus x and plus x. And at equilibrium, we're going to get 0.5 minus x, and x. Now, the equilibrium constant for this reaction would be the concentration of the acidic form. I'm going to abbreviate it as the COOH form to not write down all of the structure of the amino acid, times OH minus divided by the COO minus form of my amino acid. And guess what? This corresponds to Kb. Substituting the values that we get at equilibrium, this is equal to x, 0.5 minus x. Now, we are given the value for Ka, so we need to get Kb. Recall that Ka times Kb is equal to Kw. So, from here, we know that Kb will be Kw, that is 10 to the minus 14, divided by Ka. So, 10 to the minus 14 divided by 6.92 times 10 to the minus 3, giving a value for Kb of 1.445 times 10 to the minus 12. So a very, very small value for Kb. 445 times 10 to the minus 12. Now, we can make the approximation that since we know that Kb is very small, we know that the fraction of x, it is also going to be small. So the approximation that we're going to make is that 0.5 minus x is going to be approximately 0.5. And in general, that is going to be true whenever we find that x is lower or equal than 5% of my initial concentration of 0.5 molar. So let's verify that. With this, our equation becomes Kb is equal to x squared divided by 0.5. So we can get the value for x. It will be the square root of 0.5 times Kb. The answer gives us 8.5 times 10 to the minus 7, which indeed is much smaller than 5% of 0.5. Now, what does that x means? That x means the concentration of OH minus, that is the concentration of at equilibrium that we get of my OH minus ion. So we can calculate the POH. Recall that the POH is equal to minus the logarithm of the concentration of OH minus, in this case, minus logarithm of x, giving us a value of 6. That means that the pH, which is equal to 14 minus POH, should be equal to 8. Okay? Uh, and actually, if we do not round up anything here, over here we would get 6.07, depending on how finicky is your professor. And for pH, if we do not round up anything, it would be 7.93. And this would be the final answer for our question. The pH is 7.93 because the POH corresponds to 6.07. And that would be all. Thank you very much.